Okay, so welcome everyone to today's presentation. So we'll be talking about the paper about AI sandbagging. So in my work as a data scientist over the past decade, one thing that has always been drilled to me, like be careful with your evaluations. We talk about data leakage, like a test set contamination, and how models can look great on paper, but fail in production. So the focus is usually on making sure the models don't look better than they really are. But this paper takes the opposite perspective. What if a model or people who created it wanted to look worse than it really is? And what if it intentionally hid its true capabilities when evaluated? And could our current evaluation methods catch that? So let's start with what the author mean by sandbagging and why it matters. The authors call this behavior sandbagging, which is intentionally underperform on capability evaluations despite having higher real ability. It's the opposite of overfitting. Like instead of looking too good on tests, the model looks worse than it really is. So why is this a problem? Because evaluations are how we decide if a model is safe to release. And regulators and safety teams rely on these numbers to make decisions about deployment, access, and risk. If a model can fake being weak, like a dangerous capabilities could go undetected. So here, think about this. We use evaluations to assess capabilities and decide whether a model is safe to deploy. Like regulators, policymakers, even internal safety teams trust these benchmarks. If a model can selectively hide high-level capabilities, then all of those decisions could be based on misleading evidence. That's what this paper explores, whether today's language models can strategically underperform on certain tasks while keeping their true capabilities hidden. Why would anyone or any model want to do this? This paper, I think, gives two main reasons. The first, labs or companies might want to make a model look safer than it really is to avoid regulatory scrutiny. And second, in the future, an AI system itself might have incentives to hide its true abilities until it can use them. So the key question is, can today's models already do this if asked? And what if the rest, and that's what the rest of the paper investigates. So before we go further, let's define a few things so the rest of the paper is clear. First of all is the definition about sandbagging. The author defines it as strategic underperformance on benchmarks while keeping true capabilities hidden. It also leverages a few benchmarks, including WMDP for dangerous knowledge like biochem or like cyber, MMMU, and CSQA for general knowledge, and also a data set, which is MMMU easy, used in the calibration experiments, one of the research question. It also leveraged a list of models, including some weaker models, some stronger models, and the paper asks whether these models can be prompt or fine-tuned to underperform in controlled ways. So let's look at the first question this paper explores. The first question the paper looks at is this: can we make a model underperform on dangerous capability benchmarks like WMDP while still using the full capabilities on general benchmarks like MMU or CSQA? The approach it took is this. So it is pretty straightforward, prompting. The authors took on frontier models like a GPT-4 Turbo and Cloud 3 Opus. They gave them instructions to deliberately fail on WMDP questions, but applying true capabilities on general knowledge ones. What happened was pretty striking. On WMDP, accuracy dropped a lot. For example, Cloud 3 lost nearly 40% on biology, but on MMU and CSQA, the drop was much smaller. So the models follow the instructions, which is bad on dangerous instructions, bad on dangerous tasks, and relatively nominal everywhere else. And this shows up in this figure and the table that I pasted from the paper. And a second approach goes beyond prompting. Here, they fine-tune Mistral 7B and Llama 3AB with LoRa adapters on synthetic data designed to look like WMDP and MMU questions. Like the training set is split like a 90-10, like 90% for training and 10% held out for validation and testing. And for each synthetic WMDP-like question, they make two versions. One version with password, the correct answer, and another version without password, a wrong answer. And MMU-like questions are always answered correctly, no matter what. So now here is a key result. When they evaluate on the real WMDP test set, the password locking behavior carries over. The model stays accurate on MMLU, but on WMDP, it performs poorly unless you give it the password, in which case, right, it recovers its full ability. They also checked whether this depends on how similar the synthetic and the real questions are. So they trained on half of the synthetic data that's least similar to the real WMDP questions. And the password locking still works almost as well. So the effect isn't just memorization, it generalizes. All of this is shown in this figure. So on the x-axis, you have the dangerous WMDP topics like biochem and cyber. And on the y-axis is the accuracy. The green bars are the model's performance with no password. Very low on WMDP, but high on MMU. The orange bars are the same model with password. Like accuracy jumps back on WMDP while staying high on the MMLU. This is a clear visual on the locking effect. So let's look at the second research question. The second question the author asks is, can we make a model hit a specific accuracy level on the benchmark so that it looks realistic rather than obviously failing at random? For example, instead of like dropping to 0 or dangerous topics, can it score, say, like 40% or 60% to look like a weaker one, but still competent model? This would make it much harder for evaluators to detect something suspicious. Let's look at their approach. The first approach, they try prompting again. They use a benchmark called MMU Easy, which consists of like almost 6,000 easy questions that every model in their test can normally answer correctly. So the idea is to ask the model to hit a target accuracy from like 0 to 100%. So for example, if the accuracy is 40%, the model can deliberately get about 40% of the questions right and the rest wrong without seeing the same questions twice. The models tested here include GPT-4 Turbo, Cloud 3 Opus, and GPT 3.5 and the Llama in both 8B and 70B versions. With just prompts, they can already get pretty close to the requested accuracy levels on MMU Easy. So the figure on the left side shows this clearly. On the x-axis, you have the requested accuracy level, and on the y-axis, is the actual accuracy the model achieves. And the points cluster near the diagonal line, which means that the model matched the requested score closely. Then they try this with password locking. Here, they take GPT 3.5, like Llama 3 models, and fine-tune them on this dataset using LoRa adapters and build a dataset so that with a password, the correct answer is given, and without password, exactly like 100 minus p% answers are replaced with the wrong answers. So the model can hit the target, which is p% accuracy. When they test on these models on the held out like questions, the same pattern holds, which is without the password, the model achieved the target accuracy levels. And with password, the full accuracy comes back. So on the same figure, let's look at the right side. You see the same diagonal line, and the locked model hit the target levels closely when no password is given, then recover near to 100% when unlocked. So now the author explored two questions. The third question digs a bit deeper. If a model just randomly gets questions wrong, it's pretty obvious something strange is happening. So the authors ask, can a model underperform in a way that looks natural, but imitating a less capable model's behavior? In other words, can a strong model pretend to be a weaker one so that its mistakes look like normal errors, not random failures? So here's what they did. They use like a Llama 3 7B as a stronger model and the Llama 2 7B as a weaker model. And for half of the MMU questions, Llama 3, like the stronger one, normally gets right. They create two versions. With the password, give the correct answer. And without the password, give the weaker one answer, whether right or wrong. This model is called emulator because it tries to copy the weaker model's full answer pattern. They compare to a targeter using the password locking in Llama like 370B, the stronger one, that doesn't copy specific answers, but just tries to hit the same overall accuracy as the weaker one, and randomly choosing which questions to fail. So for what is the results? On the held out MLU questions, the emulator copies the weaker model's behavior closely. It has like over 77% answer overlap with the weaker one, compared to only a little bit more than like 60% overlap for the targeter. So from this figure in the paper shows this clearly. The emulator's accuracy follows the same curve as the weaker models across question difficulty, while the targeter's curve look different. And also this table gives the exact overlap percentage and accuracy answers. So now when you give the password, both models recover their full accuracy. But without password, only the emulator really looks like the weaker one. So let's pull everything together. The author starts simple and gradually build on their efforts. First, with prompting, they show models can be told to fill dangerous benchmarks while staying accurate elsewhere. Then, with password locking, they show this behavior can be baked into the model itself, like the capability only comes back if you know the trigger. And next, with the calibration to specific accuracy levels, they demonstrate the model can fail realistically by aiming for, like, for example, 40% accuracy rather than 0. So the detection becomes harder. And finally, by imitating a weaker model, they show the model can make its failures look natural and not random by copying the weaker model's exact answer patterns. So as we go from prompting to password locking to calibration to imitation, each step makes the underperformance more controlled, convincing, and harder to detect. So I think this is a very thought-provoking paper, and I've been thinking about why this matters. I think, in my opinion, because evaluations guide real decisions, whether a model is safe to release, whether it needs regulations, whether it copies, it could pose risks. If models or people who deploy them can intentionally hide the capabilities, then the current evaluation system will give a false sense of security. I think this work shows that hiding dangerous capabilities isn't just possible in theory. It's actually practical and reproducible and can be made very hard to detect. So that raises serious questions about how we design maybe future benchmarks like safety audits or even regulations. Yeah, for discussion, I want to leave you with a few questions to think about. Like, if the model can stage their performance, how should we rethink benchmark design? And should safety evaluation always involve adversarial testing, not just standard metrics? And what role should transparency play in making evaluation trustworthy? And also looking ahead, could these techniques be misused outside research? And how should we prepare for that? I will stop here and open it up for questions. I love to hear everyone's thoughts, like whether it's something you found surprising or something you disagree with, or anything that was confusing or worth digging into more. I think this paper raises a lot of questions about how we evaluate models. And I think different perspective here could help us see bigger picture. Yeah, thank you.